This is our exponential models day, but first we'll do a quick warm-up here. So factor using the area model, just a quick fraction question, and then again, what do you think x is 2 to the power of something is 32? You can guess and check that, and just by using your calculator. So if you remember from last year, exponential models, these in a table of values, the growth or decay factors are equal. The graph represents an exponential curve, which is something that either goes up and up and up and up and up forever, or down and down and down and never reaches zero. Remember, if I have half of a cookie and I eat half of my cookie every day for the rest of my life, theoretically, I will never run out of cookie. The graph can be written in the form y equals ab to the x, where a is the initial value and b is the growth or the decay factor. X is the exponent, and we're going to talk about the difference between a growth or decay rate and a growth or decay factor. So we're not going to look at first and second differences in this case because that's our way to remember check if it's linear or quadratic. In this case, we're just checking to see if it is exponential, which means we're going to be looking at is the rate changing at the same rate. So to look at the rate of change, we see this is a decreasing, the first one is a decreasing function. And so we're looking to see, does it decrease at the same rate? So in order to do that, we are doing division. So what we do is we take the, because we know that it's going down, so we take the lower number and divide it by the bigger number in this case. So 25 divided by 35 is 0.71428. The 15 divided by 25 is 0.6, and 5 divided by 15 is 0.33. So therefore, these rates of change are not equal, right? So the decay in this case is not consistent. If it were consistent, it would be 0.71428 for each one. So each one would be 70% of, or 71% of the one previous. And so this is not exponential. Now what we could do, we're not going to do it here, but you would then take first differences and second differences and see if it were linear or quadratic. So this next one is growth, right? So it's growing, it's going up each time. So again, we'll take the larger number and divide it by the smaller number. And you'll see in this case, now they are equal. So this one is exponential, and it is because each number is 1.25 times larger than the one before, or it's growing at 125% each time. Right, so in this case, the ratio of changes are equal. When we look at the graphs, remember we talked yesterday about how in order for it to be quadratic, it has to have a distinctive maximum or minimum in order for you to be sure. So from a graph, we are looking for, is there a maximum or a minimum? So is there a turn point? And for exponential functions, there is no turn point. Of course, for linear, there is also no turning in the data. And so this is linear or not exponential for sure. And the one on the right does grow exponentially. We can see that if we really want to. We can look at this and say, okay, so that's 2. That doubled to 4. And then that went up to 8. So you can see each time. So I started at 1, and then I doubled, and then I doubled, and then I doubled, right? So that's a double, that's a double, and that's a double. That's what makes it exponential. Exponential equations should be really easy to identify. They are when the exponent is the variable. It is the only time that the exponent is the variable. So in this case, when x is the exponent, or in the exponent in some capacity, that is an exponential function. Notice this has an exponent, but x is not the exponent. So therefore, this is not exponential. It is quadratic. And the other one is exponential because the exponent is in the variable. Sorry, the variable is the exponent. So this is a population grows by 1% each year. By what factor is each population multiplied? So if it is growing by 3%, you're going to have 100% of what you started with plus another 3%. So when it is a growth, you are growing at 100% plus the percentage of growth. You have this concept when we're calculating taxes. You know that you can multiply your purchase price by 1.13 and calculate your after-tax cost in one step because you're paying 100% of the price plus 13%. Well, same thing applies to an exponential growth. So if population is growing by 5%, it means that we're having exactly what we started with plus 5%. So any growth, exponential growth, is going to be greater than 1. So if we wanted to look at this in terms of decimals, right? 103% as a decimal is 1.03. 105% as a decimal is 1.05. So for it to be a growth, the factor has to be larger than 1. 12%, same idea. It's going to be 1.12 or 100% plus 12% or 112%. So this example, we got 2 colonies of bacteria, each start with 100 bacteria. That is the A factor. Remember in the equation, y equals AB to the x. 100 is what we start with. Colony A doubles every hour, so that means that B is 2. Colony C triples every hour, so in that case, B equals 3. So here are equations, colony A and colony B. We're going to graph the equations on the same screen. How do the graphs compare? So we can put that into Desmos. I'm just going to sketch them. There we go. I also just quickly did it in Desmos. How would the graph for colony A change if there were 200 bacteria initially? Well, remember that the initial value is where it starts on the y-axis, so colony A would just shift up, and then it would grow faster because we are starting with more, so we're doubling more every time. Here's determine the exponential relation y equals AB to the x that best fits this data in the table, where x is the number of years since 1921. So remember, we're not using the years. So the years are going up by 10, which means that 0 is going to be 1921. Sorry about that. And then 10 will be 31, 20, et cetera, et cetera, et cetera. And it's the population in millions. So we're going to look and see what do values A and B represent in this situation. So we need to figure out how much this is growing by. And it's growing, so we're going to do the larger number divided by the bigger number. We'll do that across the table to see what our growth rate is. So populations are not consistent, right? Populations are gonna ebb and flow. Some years are gonna have more babies than others, and some years you're gonna have more people die than others. So this is why we look at these things over long term. Now, what we will also do eventually is put this stuff into Desmos and let it tell us. But in the meantime, what we're going to do is we're going to take the average of all these changes and find a way that best represents this data. So we're looking at the average change over these 10 years. Sorry, 80 years. So when I round my answer, which is 1.29625, I'm going to round it to 1.30. So this is going to give us an average population growth of 30% per year. And of course, we're going to start with our 1921 population, which in millions was 0.52. Our growth rate is 30%, so our growth factor would be 1.3. And so this is going to give us an equation of y equals 0.52 bracket 1.3 to the power of x. And we can use this to estimate the population of British Columbia in 1985. So how many years has passed in 1985 from 1921? Remember, we are doing these in decade chunks, so we're going to have to divide that 64 by 10, and this is going to match our chart. So when we pop that into a calculator, we get 2.79, which if we look in here is not unreasonable. Looks like it's around there, right? Because we had 2.82 in 1981. I realize that it's going up, but we're also averaging, because we have to look back and see that some years were bigger growth than others, and so not too bad.